All righty. I think hopefully that is all right. All right. On to the exciting world of acids and bases. All right, so remember from Chem 1, acids taste sour. So like your fruits, those are acidic. They usually have citric acid in them. Sour Patch Kids have citric acid on them. There's actually some kind of acid that, I don't remember what kind of acid like put on, is on warheads. Is there like a, is there a sour warhead? No. There's something else that's more sour than Sour Patch Kids. I can't remember what it was. Huh? Is there a warhead that's like that? So it's even more acidic. It's more acidic than citric acid. Our bases, sometimes you'll see they're called alkalines. They taste bitter. They feel slippery. So this is where most of our like cleaning materials fall into. So we look at 3 different definitions of acids. Arrhenius is going to be our strictest. So that would mean Lewis is the broadest. Lewis accounts for all acids, like our normal acids that we think of, and then also kind of our other acids that don't necessarily, or especially bases that don't necessarily have the hydroxide in them. And then Bronsted-Lowry is the most common. That's the one that has the conjugates, and it's the one that, you know, throughout this unit will work the most with. So if you remember, a hydronium ion is the H3O. Sometimes you'll just see it written as H+. It's formed from a reaction of a proton with a water molecule. So a lot of times the water will just be left out. So that's why it's written as H+. Remember, if something is aqueous or if it's in solution, then that means it's going to be mixed with water. So then you're going to see the ionization. The more you increase the hydronium, the concentration, the more acidic it becomes, and the lower your pH number will go. Because remember, on your pH scale, lower end is acidic, higher end is your basic. So if y'all remember from Chem 1, so this would be under the Bronsted-Lowry definition. By definition, a conjugate, let's do our acids first. So Bronsted-Lowry, an acid donates an H+, a proton, and that proton is as an H+. A base accepts that H+, that proton. So here, if we look at HA, so that's representing some type of acid, because acids are going to start with hydrogen. It goes from HA, which would be the acid. It loses a proton, and then it becomes the conjugate base. This conjugate base should be under there. Conjugate acid should be under here. So the conjugate base is going to be everything that remains of the acid molecule after a proton is lost. And then your base would do the opposite. It goes from H2O and it's going to accept an H+, and it becomes H3O+. So acids go from being an acid to being a conjugate base. Bases go from being a base to being a conjugate acid. Bases are written, acids and bases are going to be written as your reactants in general, and your conjugates will be written as your products in general. Sometimes when it's a reversible reaction, you have to read kind of what the problem is asking you, because sometimes they may be talking about the reverse reaction. All right, so if we look at this one and the following, label yours with its acid, base, and then the conjugate acid, conjugate base. So if we look at our HBr, it goes from HBr to just Br. So it's the one that donated proton as a hydrogen ion. So this would be my acid, and it becomes your conjugate base. And then here my ammonia went from NH3 to NH4. So it accepted. So this is my base, and it's its conjugate acid. So the difference between the original species, whether it's an acid or a base, and the conjugate that it forms is going to be an H plus. That's the difference. An acid's going to be one less H plus, a base is going to be one more H plus. So notice that doesn't just change the fact of how many hydrogen you have. It's a +1 charge. So that also changes the charge. So that's why this went to a +1 and this went to a -1. All right, so on this one, I have H2S. So they're saying this is my acid. What would be its conjugate base? So, I'm sorry? Well, whenever we only lose one hydrogen at one time. So it's not going to lose both of them. It's going to start off just losing one to begin with. So it would be HS -1 because it's lost that one. And we really didn't differentiate. And there's going to be a few things you'll see that we really didn't differentiate in Chem 1 that we'll kind of go more into in AP chemistry. All right, so what is the conjugate acid of NO3-? So if this is my base, it has to gain an H plus, so it would become HNO3. It had a -1 charge, so now it would be neutral. Y'all remember that a little bit from Chem 1? All righty. Of course, there are Ks for acid and bases. We've been doing Ks for, oh, let's look at this one first. This is a good one. This isn't on your thing, just look at it. So we have our equation right here. And it says, which of the following represent the base conjugate acid pair in the equation shown above? It's the only one that makes sense, right? This question, you should have been able to kick these three out. It doesn't make any sense to have HCO3 with H3O plus. We said they only differ by an H plus. And all of these differ by much more than just an H plus. The carbon is going to be the big difference in all of them. So there's no way that could be any kind of conjugate acid-base pair. All right, so our Ka, A stands for acid, is going to be our hydronium concentration times our conjugate concentration divided by our intact acid. So this will look at just a real basic equation you would get this from. This is going to be my acid. Oops, what was I spelling there? I have no idea. And we're going to combine it with water. And we're going to end up with our conjugate base plus our H plus concentration. So this H2O plus, it's what gains hydrogen in this case, but instead of writing it as H3O plus, you'll see it usually written as just A plus, H plus. Those two are interchangeable. So it says, why isn't the water included in this Ka expression? Anybody? because it's a liquid, exactly. And if you go back to our original rules, the liquids, its concentration isn't going to change that much. It's mainly just going to be there to cause this strong acid to ionize. All right. So a strong acid mostly disassociates. The equilibrium lies far to the right. A strong acid yields a weak conjugate base, much weaker, that should say much weaker than H2O. H2O is amphoteric. We'll write that down in a minute or somewhere here in your notes. That means it can act as an acid and a base. So a weak acid is going to be mostly undisassociated. So here my HA, which would be my intact acid, is going to be less than my conjugate base because most of it's going to ionize. We're going to go mostly to the product. Here it's just going to be different. There's going to be a lot of intact acid and not as much of the conjugate base. So if I have a weak acid, it's going to lead to a strong conjugate base. Stronger than water, not in the list of strong bases. If you remember, our strong base is going to be our group 1 and group 2 hydroxides, except for beryllium and magnesium. So we're not saying it's that strong, but it's a stronger base than the acid was strong with regard to it being an acid. And that's something that sometimes people get a little bit mixed up with. We're just, when we say it becomes strong, that's in comparison to the acid it was to begin with. And if you go kind of down to the bottom of your page on those notes, you have your common acids. There are 6 of them, and those you need to memorize. So when those are put into an aqueous, into a water solution, then they're going to disassociate almost 100%. If you have a strong acid or a strong base, the calculations for those are a lot easier. Whenever you start having your weaks things, that's when they get a little bit tougher to calculate. So the weaker the acid, the stronger its conjugate base, and vice versa. And this is just kind of showing those in a chart. Same thing. If I have an acid and it's very strong, then whenever it gives away its hydrogen, gives away its proton, what's left over, the conjugate is going to be a weak base. I think there's just one more showing you that. All right. So on here, we got 2 beakers. I want you to sketch what 5 molecules of hydrofluoric acid and what 5 molecules of hydrochloric acid would look like in the beaker of water. You don't have to put any molecules to represent the water. One is a strong acid and one is a weak acid. This could be a typical question you might see on the FRQ. They would like this question. All right, so which one of those is my strong acid? Hydrochloric acid, okay? So how would you do those molecules? So let's say this is my hydrochloric acid molecule. How would that be if I put it into solution? It'll all disassociate, it'll break apart. So I should have 5 separate big ones somewhere floating around and 5 separate little ones floating around. Now my HF is weak, so we'll say the same thing. This represents my HF. So what would that look like in water solution? Yeah, almost all of it would be stay together intact. So we'll say since we need 5, let's make 1 ionize and keep another 4. We'll keep another 4 of them together. If you would have happened to put water molecules on it, that wouldn't have made it wrong, because there would be water molecules around. You probably, if you chose to do that, like if you saw this on the real AP test, then you would want to put the fact that they would be surrounding the different molecules. All right, anybody have any questions on that? So that's kind of in the middle of your notes. If you look right above that, it says a weak acid strength can be compared by looking at the Ka values of the acid. So that's one of the reasons I went ahead and gave you the sheet, although we really might not look at it that much. So the smaller the Ka value, the weaker the acid, because your Ka value is telling you how much is going to disassociate as it becomes a product. So for a weak acid, that's not going to be very much. If you look at that formula at the top, for a weak acid, you're going to have a whole bunch of your denominator. So that's going to make your Ka a small number. Strong acids do not have Ka values because the intact acid is so small that it cannot really be measured accurately. So if you look kind of at the top of your list, you'll see some of your strong acids listed on this chart. And if you look across, they don't have any Ka values. And once again, that's because the HA, the intact acid, is going to be so small, it's going to kind of end up being negligible. All right, there's a much prettier picture of that than what I drew. I should have just clicked. All right, so let's look at these. Oh, not that way. I forget to do that. All right, let's look at these. And okay, we're going to range the following species according to their strength as a base. So we want to go from the strongest base to the weakest. That's how we're going to. So if I'm at the strongest base, and that means that's going to be my weakest acid. Because if you look here, that's what I'm looking at. These are all conjugates of some acid. These are all conjugate bases of some acid, except for the water. So that means I need to find my weakest acid and I need to go to my strongest acid. Okay, so I'm going to say what they were. H2O was obviously still H2O. It became HF. This came from HCl. This came from HNO3, and this one came from HCN. That was their original acids. So which one of those is our strong acid? HCl. So that means that conjugate base is going to be the weakest. So I'm going to put it on my weakest side. Then after that, water would fall after that. And then for my next, and this says 20, this should say 10 to the -4. So then the 3 that I have left over, they're all weak acids, so I can't look at them this way. So now I have to start looking at their Ka values. So by far, which one of those has the very smallest Ka value? Yeah, this one right here, my HCN. So that means it came from my CN. So I need to put my CN on this side. It was the weakest acid, so it's the strongest conjugate base. All right, then we have 7.2 times 10 to the -4 and 4 times 10 to the -4. So what would come next? My HNO2 or my HF? Remember that the next, yeah, this one, because we're going from, we want to go from the weakest acid to the strongest acid, because we're trying to actually do the bases, but we don't have information for bases. So this is my next smallest number. So that means my NO2 would be next. And then somewhere in between there, I would need to put my fluoride ion. So when you originally were given these, you don't have enough information to know what kind of bases they are by themselves. So you're going to have to approach it some other way. So in this case, you would have to add a hydrogen to all of them, which would make them then an acid, and then you have acid information that you compare. So your strongest, whatever strongest acid you had in there, that's going to end up giving you the weakest conjugate base. So that was why the chlorine was down there. That makes sense? Whether it makes sense or not, can you follow that? I guess would be a better word. All right, common strong acids. I feel like I've said to memorize these before. Now you really need to memorize them for sure. Most of them are mono. All of these are monoprotic. And this one is diprotic. Anybody remember what that means? How many hydrogens they have? So all of those just have one, and then my sulfuric acid has two. Acids donate one protein at a time, proton at a time. And evidently my mind's already gone on spring break. One proton at a time, and like I said, we didn't really make a big deal about that in Chem 1. We kind of just looked at the big picture. And usually the first proton contributes more to the acidity of the solution, the second or third proton not as much. All right. So sulfuric acid is a diprotic acid, which means it has two acidic protons. The first one is strong and the second one is considered weak, which I feel like I kind of just said. I guess I probably jumped ahead of myself. And then this kind of tells you what you have: monoprotic, diprotic, and then after that, polyprotic, which phosphoric acid is going to be your most common one of that. If you remember oxyacids, most acids are oxyacid. So that means the hydrogen is combined with a polyatomic ion. Those are the ones that do not start with hydro. So the acidic acid is attached to the oxygen, because sometimes they may have other hydrogens in there that are just part of the formula, but are not considered acidic acids, or they're not considered acidic hydrogens. So these would be some of our weak oxyacid, the phosphoric, nitrous, and the hypochlorous. And if it's not strong, then it is considered weak. Within a series, acid strength increases with the increasing number of oxygen atoms. Because if we talk about acid strength, that's the E's. It loses an H plus. So anything that's going to pull the electrons more toward itself and away from the hydrogen, that's going to make it a stronger acid. A lot of times the hydrogen is attached to the oxygen. Oxygen is pretty electronegative. So the more oxygens that I have, so here we have our chlorous series going, starting here we have perchloric, and then going all the way down here to hypochlorous. So the more oxygen it has, the stronger it is. And then here, same thing, we have sulfuric and sulfus. Sulfuric is going to be stronger than sulfurous because it has those 4 oxygen. So once again, that's going to pull the hydrogen away more, and they're going to be easier to disassociate. Electronegative oxygen draws electrons away from that OH bond. And the more that they're able to do that, because they have more oxygen, then the easier it is for the hydrogen to leave that bond or to disassociate, however you want to think about it. Actually, let me go back there and see if that's the one I want. No. As far as you're looking at acid streaks with increasing electronegativity of oxyacids, here we have chlorine, bromine, iodine, and then here you would look at carbon. So you can see the more electronegativity is, because chlorine is more electronegative than bromine. If you look, fluorine is the most electronegative. Remember, it had a 4, and we're going to talk about in a minute why it's not listed. So just going down, chlorine's going to be more electronegative. So once again, pulls the hydrogen, those shared electrons more toward it, away from the hydrogen, so the hydrogen can disassociate more. Does anybody want to take a guess why fluorine is not in there? Its high electronegativity makes it say it should be in there. But if you think about it, fluorine is the smallest of all of those. And so then that means that hydrogen is able to get closer to it. So that like breaks right at fluorine. Now, once you get to chlorine, they start getting, that atom gets larger. So then that rule is bypassed. So that only works for the HF. That's why it's not in this list right here. All right, organic acids. Those, we don't use those a lot. Probably the most common one that we have is acetic acid. And so this is kind of what I was talking about. That formula is CHCOOH, but it only has one acidic acid. It is monoprotic. So this would be my structure of that. So the one that it is will lose, or the acidic hydrogen, is that one right there, the one that's bound to the oxygen. The ones that are bound to the carbon, hydrogen, pretty similar electronegativity, so those are going to be held tighter. Benzoic acid, same thing. This, it may have some other hydrogens in there, but this one is going to be the acidic hydrogen, because even though it's not written there, it's like this. So even though an acid may have some other hydrogens that are part of the formula, the one that is going to be bound to the oxygen is going to be the one that it loses. And probably acetic acid is our most common one. Hydrohalic acid, so that is if hydrogen is attached to a halogen. Those kind of have a little special name. HF, if you look at your list of hydrohalic acids, there's only one in there that is considered a weak. All the other ones are on your strong list. And that's what I talked about before. It's the only weak hydrohalic acid. And even though that's a very polar bond, because we know fluorine is very electronegative, fluorine is very small. And so the acid does not completely disassociate. The hydrogen kind of bunches up to that fluorine and is held together pretty tightly. All right. And I think we already went through this. We got the acid strength is compared by the Ka values. The smaller the Ka, the weaker the acid. And yes, we talked about that already a little bit earlier. So amphoteric substances is something that can act as an acid or as a base. So your typical one is your H2O. NH3 is also amphoteric. HSO4, so that's your sulfuric acid after it's lost one hydrogen. That also would be considered amphoteric. Anything that can both accept and donate a proton are going to be considered amphoteric. So if you look at H2SO4, so sulfuric, it's going to lose one hydrogen first. So that's where you end up with your HSO4. So then that HSO4 can lose another hydrogen. I lost my charge there. Another hydrogen. So that's why it's amphoteric. It can go this way and it'll accept that hydrogen and go back to H2SO4, or it can go this way and lose another hydrogen. So like I said, typical one is your water. Elliot, if you're going to sleep in my room, go back there and sleep somewhere so that when somebody walks by, they don't see you laying your head down. Because I'm not prepared to get in trouble for your lack of care about this class. All right, water goes through something that is called autoionization, which means anytime we have water together, it's not all H2O molecules. They're going to, some are going to act as acids, some are going to act as bases, so some are going to lose hydrogen, some are going to gain a hydrogen. So we would have a mixture of all three of these things. If we drink a glass of water, we're getting all of these. Oops, that should be H3O plus. So why then, if we're getting H3O plus, why does it not hurt us when we drink a glass of water? Is it what? Yeah, small concentration. It's so small and it's equal. Remember, H3O plus kind of represents the acidic part of a compound. OH minus represents the basic part. So in water, those are equal to each other, which ends up being neutral. So that's why we can drink our water, even though all those things are floating around in there. Well, that usually is probably because some kind of minerals are dissolved in it. Or not just minerals. I mean, I guess sometimes worse things are dissolved in water, but you might not want to think about that. All right, so the ion product constant for water, which is represented by Kw, is going to be your hydronium concentration times your hydroxide concentration, and at 25 degrees, because Kw differs with temp, then it is equal to 1 times 10 to the negative 14, which means that may be a formula, or that relationship may be something that you can use to solve some problems. I tried to go through and mark what we have for pH on here. And that one is on there. So under, when you look at your green sheet, under equilibrium, that's where you would find stuff for pH. It has to do with pH, acid base content. So this is actually is on your green sheet. All righty. So we kind of already touched a little bit about that. No matter what an aqueous solution contains at 25 degrees, those two are going to be always a product equal to 1 times 10 to the negative 14. So our neutral solution, they're going to be equal. We should get a pH of 7. Our acidic solution, the hydrogen ion concentration or hydronium concentration is going to be greater than the hydroxide. So we're going to get a pH greater than 7. And then vice versa, we're going to get a of less than 7. And I kind of already said that, but pH does differ with temperature. All right, I think we can get through one more page, which was my plan. All right, so there's some formulas. Hopefully you remember some of them from Chem 1. And this is used to find either your pH or your pOH. There's some typos on this one. I think it's correct on your notes as far as it's supposed to be a small p. So that I'm going to put, or you can look, you don't have to store them if you don't want to. I'm just putting the one that are actually on your green sheet. So any of those that I stored are on your green sheet. These two aren't. So this one and this one, or if you know the pH or if you know the pOH, then you can use that information to either find your hydronium concentration or your hydroxide concentration. And that's just by taking 10 and then raising it up to your negative pH, or 10 raised up to your negative pOH. Those two were not on there, but they're not too hard to remember. Yeah, if it's, yes, it's related to that one. So just showing you our scale hydrochloric acid. You can see lemon juice, stomach acid. So it doesn't take, I mean, lemon juice, I mean, you know, we probably, anybody like to eat lemons? I don't know, but that has to me a pretty low number, but it kind of just puts it in perspective. Sodium hydroxide, ammonia, they get up there a little bit higher. Sodium hydroxide, 1 molar gets all the way up there to 14. And pH numbers, if you remember from Chem 1, are logarithmic numbers. So that's why the concentration, oh, I really don't know how to explain that, but that's why you, based off your concentration, you get a number that doesn't seem too represented. I don't know how else to say that. I believe in a minute here on the slide, it kind of says it better than that. If y'all remember sig figs with pH and other log values, I don't know if other log values we do, the number of decimal places in the log value should be equal to the number of significant figures in the original number, which is usually a concentration. So pH is equal to 4.42. How many significant figures would that be? It actually is not 3. That's a little tricky thing about it. Exactly. Remember from Chem 1, it's just, I know it's been a while. Well, and y'all three, probably at this point, we were on Zoom doing this. So it's you look at the places behind the decimal. So this is 2 sig figs. So that meant I probably got that from a concentration that had 2 sig figs to begin with. So just look at places behind the decimal. The whole number in front does not count as a significant number. All righty. Oh, this is what I was trying to say, but this says it much better. pH and pOH are logarithmic functions. And so the pH changes by 1 for every power of 10. So that's why they kind of don't seem to be related, if you can think about it. So a substance with a pH of 3 has 10 times the hydronium concentration as a substance with a pH of 4. All righty, because you were wondering that. So calculating the pH of strong acid solutions, that's going to be easier than once we get to weaker ones. It comes a little bit harder. So it's usually very simple. The pH is simply calculated by taking the negative logarithmic or log of the concentration of a monoprotic strong acid. So for example, if I have hydrochloric acid, it's going to ionize into H plus Cl minus. If I know this is 1 molar, then I know these are also 1 molar. And that's because it's a strong acid. So then if I had the concentration, then I could use my formula to get the pH. So the pH of a 0.1 molar solution of hydrochloric acid would be 1. Now this is going to be different than what we did in Chem 1. However, if the acid concentration, even if it's a strong acid, especially if it's a strong acid, is less than 1 times 10 to the negative 7, which if you go back and you look at the auto ionization of water, that's where that number comes from. If it's less than that, then the water is what is going to be contributing more or more important to the source of the H plus, and the pH will be 7 or neutral. So if I have my hydrochloric acid and it's 1 times 10 to the negative 7, my pH is going to be 7. It's going to come from the water. It's not going to come from the acid. And that's definitely is different than we did in Chem 1 for sure. We didn't take it that far. So another exception is calculating the pH of a sulfuric acid solution, because that's strong. that is more dilute than a 1 molar. So that's pretty strong. At that concentration, the H plus or the hydronium concentration of the HSO4 must be calculated also. And we'll probably get to that more next week. So in other words, we almost like doing two equations. You're going to have to calculate the concentration of the first hydrogen that's lost and the concentration of the second hydrogen that's lost, but only when it's more dilute than 1 molar. All right, let's see what else. I think we might have a couple problems. All right, so calculate the H plus concentration, the hydronium concentration, and the pH concentration of a 1 molar solution of hydrochloric acid. So this is definitely stronger than 1 times 10 to the 9th. And we can finish up with that. Remind me, we're right there. All right, see y'all tomorrow. We will carry on.